So just like for the Laplace transform, convolutions are really useful for working with the Fourier transform, and they're defined the same way. So the convolution of u and v at some value, let's say x, because it's a space variable, is going to be the integral over r of u x minus tau v tau g tau, right? And so this is valid for any elements of the Schwartz class. And I should just say real briefly that there's a bunch of technical assumptions that you would theoretically need to check while doing work with Fourier transforms, like, hey, check to make sure that everything is a Schwartz class. Hey, check to make sure it's actually valid to move the derivative under the integral sign. There's like theorems that give you that. What about the conditions? Well, one of the kind of good things about differential equations is you can cheat a lot, because if you do an invalid move, but it gives you an answer, and then you check that answer and it satisfies the differential equation, then hey, you won. So what if you lied, cheated, and stole in order to get there? You succeeded. You solved the problem. So a lot of times, this is why I'm skipping over those picky steps with the technical parts. So just like for the Laplace transform, there's a convolution theorem. So the Fourier transform of a convolution is just the pointwise product of the Fourier transforms. And again, the way that we use this most of the time is when inverting. So to find the inverse Fourier transform of a product, we can split it into things it's going to come across as the convolution of the inverse transforms. And so that's how we can write down a solution. So let's take a look at an example. We'll work out u double prime minus u equals f. So just a baby example. So we begin by taking the Fourier transform. And so the double derivatives there, that's going to kick out a minus I xc quantity squared times u hat. And then u is just going to become u hat, and then f is going to become f hat. And so if we gather together what we've got on the left, there's a minus 1 plus c squared times u hat. And so we can solve for this guy. And so now we've got a pointwise product of Fourier transforms. And so we know that this is going to pull back as the inverse Fourier transform of this guy, 1 over 1 plus c squared, convolved with the inverse transform of f hat, which is just f. And so at this point, you appeal to some table, some lookup table. And you find that the Fourier transform of minus 1/2 e to the negative absolute value x is minus 1 over 1 plus c squared. So that's the thing that you'd need to convolve against. And so our formula for u then is going to be minus 1/2 integral over r, just to write out the convolution in its glorious, gory form. So we've got e to the absolute value of the difference, f of y dy, or tau d tau, whatever you want to use for your dummy variable.